Hello and welcome. In this video lesson, we're going to take a look at a method called separation of variables. So as we have already mentioned, the goal of an analysis of any ODE is to establish a clear relationship between y and t, even though you start with a model for the rate of change of y with respect to t. So often we'll write this notation here to indicate a first order differential equation, and this is just suggesting that dy dt may depend on both the independent and dependent variable. In translation, that just means that the right-hand side of the equation may have both t and or y in it. So there are actually three forms of analysis that we typically conduct, and separation of variables is one specific variation of one of these three types. So oftentimes, many differential equations are not solvable, especially as they become nonlinear, and we'll discuss what all that means in a later video. But you have a qualitative analysis, and what you're doing with the qualitative analysis is you're trying to study the general qualities of the solution. So for instance, a qualitative analysis might indicate, well, if y and t are bigger than these values, then dy dt is positive, or y is increasing if it starts off at a value of 3 or bigger. So that's qualitative in the sense that it describes what will happen, i.e. y is increasing over time, but it doesn't really tell us specifically how. Then a slightly more useful analysis, oftentimes, would be a numerical analysis, where what you're doing is you're in some way taking advantage of what you know about the differential equation to generate basically a set of ordered pairs over time. So think about numerical analysis as you're estimating values. So you are actually estimating values of y over time here. In step one, you're really not doing that. You're kind of just generally describing what will happen under certain circumstances. And then the most powerful, the one that we want to aim for, is the analytic analysis. And here, this is really what we did in Calculus 2. We learned how to solve differential equations, or basically take antiderivatives and go through the integration process to get the original y function back. So we're going to focus on one variation of number 3 here. But before we do that, let's actually discuss what we mean when we talk about, well, what is a solution to a DE? We maybe know how to find them from some of our Calculus 2 techniques, but what does it really mean once we've found it? So a solution to a differential equation of this form is a function, y of t, that makes the equation true. This is kind of like what you would have done in algebra, where you might have said, okay, well, let's look at the equation 5y plus 10 equals 20, and I might argue that y equals 2 is a solution to that. And the way you would check that is you would say, well, let me put in a 2 for y here, and if I put in a 2 for y, 5 times 2 plus 10 comes out to 20. Oh, and that's exactly what I was expecting. 20 does equal 20, and therefore y equals 2 is indeed a solution to that equation. But when we're talking about differential equation, the distinction is that the solution to this is a function that makes the equation true. Just like in solving an equation, an algebraic equation, the value, the numerical value of y that makes it true is what we call the solution. So put more practically, a solution takes a rate of change model for, say, the change in Elk per change in unit time, and gives us a function that describes the number of Elk as a function of time. Okay, so it does not only satisfy it algebraically, but it also leads us to going from a rate to an amount. So if you think about a derivative as a speed, then its antiderivative is kind of the distance at any moment. So how do we check? For example, is y equals ce to the 0.01t a solution to dy dt equals 0.01y? Well, first of all, c is our arbitrary constant, so that's the same thing that we would have learned in the Calculus 2 class. In order for this to be a solution, what we're saying here, let's interpret this. The derivative of y, and I won't say with respect to t, we'll just assume that that's the case. The derivative of y with respect to t must equal And I'll put a little must above this equal sign to emphasize that we're saying in the English language that the derivative of the function that we find must equal 0.01 of the original function y. In other words, we're looking for a solution that when you take its derivative, what you get is just some scalar multiple of the original function itself. Well, exponential functions, if you think about it, when you take the derivative of an exponential, you still end up with some multiple of your exponential. So here's how we handle this. We, first of all, in order to plug things into this equation and see if this makes it true, I'm going to need its derivative as well. So the derivative of my equation, the derivative of this using the chain rule, will be 0.01 c e to the 0.01 t. Now what I want to check is I want to check that when I plug in for dy dt, I'm going to plug this in right here, 0.01 c e to the 0.01 t. Does that equal, I'm going to put a question mark above that equal sign, 0.01 times y? Well, what is y? Well, y is the original function that we're claiming is the solution here. So I'm just going to replace y with c e to the 0.01 t. And now let's, simplify, quote unquote, both sides. The left side, there's not really much I can do. I can remove the parentheses on the right side, and lo and behold, these two sides are in fact equal to each other, and therefore the answer is yes, this is a solution because it makes the equation true. Just like up here, y equals 2 made the equation true. Let's look at another one. Is y equals 1 plus 2t a solution to this messy ratio y squared minus 1 over t squared plus 2t? So again, the first thing we need to do is if we claim that y equals 1 plus 2t is the solution, then I need to find its derivative because I'm going to have to plug in the derivative of that function. This is where this varies a little bit from what we used to think of as a solution. When we plugged in y equals 2, we didn't have to plug in any function of y equals 2. We didn't have to take its derivative. But with differential equations, it's that extra layer of complexity. Now the derivative of 1 is 0, the derivative of 2t is 2. And so now I have to say, okay, well for dy dt, if I plug in 2, does that equal the right-hand side? Well, y is 1 plus 2t, so I have to replace y with 1 plus 2t right here. That's squared minus 1 over t squared plus 2t. Well, those don't look the same, but I probably know that since there's a fraction here, something may cancel out, so I'm going to keep working on this and kind of massaging that right side. So if I FOIL 1 plus 2t squared, I'll get 4t squared plus 4t plus 1. And then I'll have minus 1 over here. That's that minus 1 right there, all over t squared plus 2t. All right, so again, I'm not sure yet whether these two sides are equal or not, but I do see that here I'll have a cancellation of a plus 1 and a minus 1. So I'll have 4t squared plus 4t over t squared plus 2t. And I kind of see that they both have the t squared in there, but the top doesn't quite look like the bottom, so it's not like I can cancel out a t squared plus 2t. I could factor out a 4 from both terms in the top and make this t squared plus t over t squared plus 2t, and that clearly will not cancel out, right? T squared plus t will not cancel with t squared plus 2t. Therefore, these are not going to be equal to each other, and so our answer is no. 1 plus 2t is not a solution to this equation. Now let's suppose we take a look at another possible solution candidate for this differential equation. Same differential equation, but now we're going to check if 1 minus t over 2t plus 1 is a solution. So I've got to find the derivative of this guy, and this is just a common step in checking solutions. If you had a second derivative in it and you thought you found a solution, it might be the case that you need to take the second derivative of y. Okay, so in order to find this guy's derivative, I have to use the quotient rule, which is derivative of the top times the bottom. So f prime g, which the derivative of 1 minus t is negative 1. times the denominator, which is 2t plus 1, and then minus the derivative of the denominator, which is 2, times the numerator, which is 1 minus t, divided by the denominator squared, which is 2t plus 1 quantity squared. Now I'm going to clean that up a little bit because I know I'm going to have to reduce things later on anyway. So here in the top I'll have negative 2t. Here I'll have positive 2t, so the 2t's will cancel out. Then I'll have a negative 1 and a negative 2, which I believe comes out to a negative 3 there. And all over the square of this. For now, I'll go ahead and leave that alone. I may not have to FOIL that out after all, but let's go ahead and check. So now we're going to go ahead and plug in for dy dt in this equation. We're going to plug in for dy dt what we just found as the derivative of our candidate solution. And we're going to check, is that equal to the square of y? Okay, so the square of y is going to be the square of this function. So 1 minus t over 2t plus 1 quantity squared minus 1 over t squared plus 2t. All right, so as we proceed, let's go ahead and do a little bit of analysis on this guy here. So first off, if we square both top and bottom, then the square of 1 minus t, if we were to go ahead and FOIL that out, we would get t squared minus 2t plus 1. And the square of 2t plus 1 is going to be 4t squared plus 4t plus 1. And we have our minus 1 all over t squared plus 2t. Now one thing that I can do here is find a common denominator. So I'm just going to continue on over here. I'm still checking about this equality, so I'll just write question mark equals, and I'll get a common denominator here. So minus 1 you can think about as 4t squared plus 4t plus 1 over 4t squared plus 4t plus 1. So in this case we have to do quite a bit of algebra to massage this down. And minus 1, like I had mentioned, is just going to be, we'll write that as 4t squared plus 4t plus 1 over 4t squared plus 4t plus 1. That's just getting a common denominator. And now we can subtract the numerators. This is all over t squared plus 2t. So you can see this just can sometimes involve quite a bit of algebra. T squared minus 4t squared is minus 3t squared. Negative 2t minus 4t is negative 6t, and 1 minus 1 is 0. And this is all over 4t squared plus 4t plus 1. Whoops, let me try that again. 4t squared plus 4t plus 1, all over t squared plus 2t. Now, because I'm going to have a fraction divided by something, I'm going to be able to multiply by the reciprocal of t squared plus 2t, so which is 1 over t squared plus 2t. And we're getting closer. I actually see that if I were to FOIL out 2t plus 1 squared, that would be 4t squared plus 4t plus 1. So I see that my denominators are the same here. The question is, will these cancel out and give me the negative 3? Well, in fact, I see that I can pull out from the numerator, I can pull out a negative 3 from both terms, which will then just leave me with negative 3 times quantity t squared plus, let's see, where were we there? And this guy would leave me with a plus 2 because we had a minus 6 there. And we can see that both of these terms cancel out, these factors here and here. And I am, in fact, left with negative 3 over 4t squared plus 4t plus 1, which is exactly the same thing that I have on the right-hand side. And again, I just had all these question marks above the equal sign. That's just a way of setting things equal to each other with the knowledge or with the guarantee that you're not claiming that they're equal, you're checking to see whether or not they are. And in this case they are, so therefore the solution up here that's been found or been given to us is in fact the solution to that differential equation. So we saw in number 2 that 1 plus 2t wasn't a solution because you didn't get the left and the right hand side equal to each other. It was not possible. But in number 3 it was possible to do it. So the next question we would want to ask is, well, how do you find that solution? How would you find it if you didn't know it? And in some cases, an analytic technique is possible for solving when the equation is called a separable differential equation. One of the first models that we saw where we didn't actually know how to solve it was the Elk model in our previous lesson, where dy dt equals 0.2 of y. And basically this just meant that the elk population was growing at a rate of 20% per year, or another way of saying it is that 20% of all elk reproduced. Another way of saying that is for every one female adult elk, 0.2 additional elk were born on average. Now here we can state that c equals 0.2t is a solution, and this can be justified in the same fashion as this exponential was a solution to this equation, but the question is, how do we find it? Now, we are going to define that if you can take the right-hand side of a differential equation and you can factor it out into 2 separate factors, one of which only has t in it, and the other of which only has y in it, then we call that equation separable. And you can see that it's now you've separated the variables from one another. Just to be super clear here, when we're saying g of t, think about g of t as a playground. And on the g of t playground, the only people or kids that are allowed on this playground are ones that at most depend on t. So if e to the t came along and said, hey, I want to come into the playground, we would allow e to the t into that playground because, of course, e to the t only depends on the variable t. If t squared came around, we'd say, yeah, come on in. You only depend on t. If 3, the constant 3 came around, we'd also let that constant in because g of t means that at most, that function can have a t in it. It can be a constant function. Any function can be constant and still be considered a function of t, but the second you throw y into it, it's no longer allowed on that playground. So if y squared t came around and said, hey, I want to come in, and say, nope, we can only allow functions of t. Kind of a silly analogy, but I find that works. Same kind of thing goes for h of y. h of y, we're only going to allow functions that depend on y into there. So, well, for example, if y cubed came along, you're welcome to come in. If sine of y came along, you're welcome to come in. If 7 came along, we'd allow 7 into that playground. So when we say separable, one of these functions could be a constant function. And to quickly look at this, let's look at a couple of examples of, is dy dt equals 3t plus 1 times y squared separable? Well, clearly it is, because it's already written as a product of 2 factors, one of which is a function of time, and the other of which is a function of y. And so I can say that g of t is 3t plus 1, y squared is h of y, and it clearly follows that form. It can be expressed in that form, therefore it would be called a separable equation. Some equations, like number 5, are not initially written in the form that we like. So we sometimes have to massage it a little bit to see if it's possible to get it in the correct form. In this case, I see that both terms contain a y and a t squared. So if I factor out say a t squared, or a y, doesn't really matter which, then I could say that t squared times y minus 6y is now a function of 2 components, a g of t multiplied by an h of y. Alternatively, another way you could have written that, and these are not unique, meaning sometimes you could have, like if I had factored out a y instead and written this as t squared minus 6t, notice that the factorization is different. In this case, I would have called g of t, t squared minus 6t, and h of y would have just been the function y. In number 6, we don't even see a y in it, and that's a good sign. Now this is something you could solve just by using your standard Calc 2 integration, because only the independent variable comes into play. But here's one fun thing you can do, and most people find this kind of mind-blowing at first, but what if I just factor out a 1? I just factor out a 1 like this, which is still a true statement, it's still the same equation. Now, based on our playground analogy, we could say that this is g of t, and we could say that this is h of y. And so our h of y is a constant, our g of t is actually a function of time. So this one is indeed separable as well. Same kind of thing goes for number 7. In this case, I don't see a function of t, but if I write this as 0.2 times y like this, and the parentheses are just there for emphasis, they don't need to be there, but this I could call my g of t multiplied by my h of y. You could actually, another way to do this would be to say, well, I'm going to write this as 1 times 0.2y, and in this case I would claim that g of t is a constant and that h of y is the function 0.2y. So again, these are not unique factorizations. Sometimes there's more than one way to do it, but as long as you can write it as a product of a g of t and any h of y, you're in good shape. Number 8 is a little bit disconcerting because I see this plus 1 here, and that's throwing things off. So I can't factor out a y, I cannot factor out a t, therefore this one is not separable. It is not a separable differential equation. So I just cannot write it. The first term is written as a factor of t and y, but I've got to be able to do it to the entire right side of the equation, as we see here. Okay, so I think that now that we're familiar with the form, let's see how to go about solving with this method. This method is, the reason we need to be able to write it in a factored form is we need to be able to divide and multiply things over. So the trick really lies in getting the y variable on the same side as the dy dt. So this is how this works. If all I do is I figure out a way to first of all factor out my equation, and we've already observed that one way you can do this is by writing 0.2 times y like this, calling this your g of t and calling this your h of y. So divide the h of y over, and that would give us 1 over y times dy dt equals 0.2. Now the multiplication piece, or rather division, which is multiplication by an inverse, is very, very convenient because now what I'm going to do is I'm going to integrate both sides with respect to t. And that's the only step that we needed to do in order for this to work out. Now the issue that we would have if we had just tried to integrate our starting equation is if we had just integrated both sides normally like this, and then we try to take the integral of 0.2y dt, the problem with this right-hand side is we're trying to integrate with respect to t, but the variable here is a y. So you can't integrate y with respect to t. And some Calc 3 people, if you've taken Calc 3, then you might say, well, I can use partial integration, but y is not an independent variable. Y is actually a function, and it's a function of time. So this variable is some expression involving t, we just don't know what it is. So unfortunately, you're not going to be able to integrate that. And therefore, by rearranging things like we've done here, what this does is we have division by dt and multiplication by dt, and this integral ends up being an integral with respect to y. You could also make an argument about that if you use u substitution here, then this becomes a u substitution problem, but I like to go with the method of the dt's cancel, and now on your left-hand side, observe that our integral is now with respect to y. So we're integrating 1 over y dy. We changed the variable of integration in this way. And it was just that one simple step of dividing the y function over. Now the integral of 1 over y is the natural log of y, And it's really the natural log of the absolute value of y. That's not going to become super important for us, but it's just a good practice. Now, anytime you integrate, you add an arbitrary constant. So I'm going to add a c here. And over here, 0.2 is 0.2t as its integral, also plus an arbitrary constant. But wait a minute, these aren't necessarily the same arbitrary constant, because when I take the derivative of the natural log of y plus any number, I'm going to get 1 over y. And same thing for the derivative of 0.2t plus c. So I'm going to keep track of these by putting subscripts here. And now I have already solved the differential equation, because the goal of solving it is you have no derivatives left. But this is not a very useful equation, because if I want to go and graph this or do some analysis, I want to get an explicit function in terms of y. So I want to solve for y. And in order to do that, I'm going to move everything else over. The natural log of y equals 0.2t plus c2 minus c1. Now here we're going to make the claim that if you take two constants that are arbitrary and you subtract them or combine them in any way, you still have an arbitrary constant. So I don't really care specifically about the value of c2. I don't really care about the value of c1. What I really care about is the result of that difference. And I'm going to assign that to a new variable, call it c, which is still an arbitrary constant. So all I'm doing is just combining constants into one constant. And I have natural log of y equals 0.2t plus c. Now we're almost at the point of solving for y. Now we're going to exponentiate both sides. So e to the power of the left has to equal e to the power of the right. Now on the left-hand side, well, the reason we did that is because e raised to the ln, those are inverse operations and they cancel. So this leaves me with just y equals, as I've desired. And here I have to be careful because the plus c is in the exponent. You cannot just write plus c down here. You can't do that because that's violating the principle of if natural log of y equals 0.2t plus c, then by exponentiating both sides, the powers still have to be equal to each other. And if you didn't write that plus c in the exponent, then you've basically violated the equality from your last step. But here's one cool thing that we can do. One cool thing that we can do is use the property of exponents. So one thing that we know is if you take x squared times x cubed, for instance, that's equal to x to the 2 plus 3. Because x squared is x times x cubed is x times x, and you basically have 5 factors, so you would have x to the 5th. But this goes both ways, right? So if I have two bases that are common multiplied together, I can add their exponents. But if I have a base with a sum in the exponent, I can break it back up into factors. So here I have that, so I can write this as e to the 0.2t times e to the c. Just again, property of exponents. And the reason I want to do that is because here I have a constant raised to the power of an arbitrary constant. And that itself will be a brand new arbitrary constant that I'm just going to label as, well, I could relabel it as c if I want to, because ultimately we're not going to ever go back to c2 and c1, but just to differentiate it from the different constants, I'll call that k. And my final answer is y equals k e to the 0.2t. And that actually agrees with what claim I made back up here, which is that if you solve this guy, you get some arbitrary constant times e to the 0.2t. We ended up having a k there, but we could have called it c. That's kind of a weird thing to want to do, though, right? Because if I had just called this C3 and C4, some people like to keep track of them. Every time they make a substitution, they give it a new subscript value, but it's really not important. You can keep replacing arbitrary constants with the same thing. So e to the c, we could have just called c once again. I know that seems kind of counterintuitive, but if it feels better, you can always make substitutions like we've done here. Okay, so that's really how the technique works. It always works the same way. The one thing to think about, though, is some people will want to do this. And this is what a lot of tutorials will show you, is what they'll do is they will separate the dy and the dt. They'll do something like this. They'll say dy equals your function of t times your function of g. I think we've called this g of t and h of y, but the notation is not that critical. And they multiply the dt over here, and then divide the function of y to the other side, like this, and make this f of t dt. And then they're like, oh, all you have to do is just slap on that integral sign, and you're good. But there's a slight logistical problem here. And the problem is that whenever you integrate, you have to specify the variable of integration. So you can't just use existing differentials and just say, well, the left-hand side is with respect to y, the right-hand side is with respect to t. Now, ultimately, this does work, but not for the reason that we're describing here. The reason this actually works is if we follow the same logic as we did up here, what we did is we divided the g of y to the other side. Whatever function that might be, we divided it over. In our case, it was just g of y equals y. And so then we have 1 over g of y dy dt equals f of t. And now, when you go ahead and integrate that with respect to t on both sides, the dt's cancel out. And that's the step that we performed here. Now, if you don't like the cancellation method, some mathematicians will disagree with that, but really what's happening here is there's actually a u substitution that can take place that will, when you take its derivative, you get a d by dt, but I like to think of it as the dy dt's cancel, or the dt's cancel, and now I'm integrating 1 over g of y with respect to y, and I'm integrating f of t with respect to t. And you notice, hey, that gave us the same answer as we got using the wrong method. And the reason I emphasize this is because this is technically mathematically valid. What's happened here is invalid because of the fact that I did not specify a variable of integration, that I just kind of used the existing differentials there. And that's not really allowed, but it does work. So just because it works doesn't mean it's a good idea. And this is if you take this approach, you're integrating both sides and you're specifying that integral variable of integration, you're not going to make the same mistakes. All right, let's get a couple more examples here. Solve dy dt equals t cubed times y with an initial condition of y of 0 equals 1 using separation of variables. So the first thing we want to do is just write it into the factored form. I already see that this is a product of t cubed and y. And what I want to do is divide that function of y over. So 1 over y times dy dt equals t cubed. Now when I integrate both sides with respect to t, I am going to get the integral with respect to t, the integral with respect to t. And now my dt's cancel, so I have the integral of 1 over y dy, which is the natural log of y, plus some arbitrary constant, c1. The integral of t cubed is 1/4 t to the 4th, plus some other arbitrary constant. Now you see that we get an arbitrary constant on the left and the right, but the thing is when we solve for y, we're always going to subtract it over. So no matter what, that arbitrary constant is going to end up on the right-hand side. And because I'll have plus c2 minus c1, I'm just going to call that plus c again. So we could have saved ourselves a step initially here because we end up subtracting the c1 over and combining the c2 and the c1 like we did here. It would probably save us a step to just say, I'm just going to put that constant on the right-hand side. I'm not going to worry about the constant on the left. We'll just put one bulk arbitrary constant on the right. Now when I exponentiate, so e to the power of the left equals e to the power of the right. E to the ln y cancels and gives me y. And here, again, if I use my property of exponents, e to the 1/4 t squared times e to the c. And once again, this is a constant raised to an arbitrary constant. So I will just write that as k e to the 1/4 t squared. Now this is called the general solution because I haven't yet satisfied my initial condition. My initial condition says that when t is 0, y has to be 1. And so if I plug in 1 for y and 0 for t, I will get k equals 1. And so that leads me to my specific solution, or my particular solution, of 1e to the 1/4 t squared. And this is called the particular solution. Particular just means that it's particular, specific to the initial condition that was given. And that's our solution for that guy. The trickiest part with doing these is just keeping track of all your arbitrary constants, but the general rule of thumb is anytime you have a constant that's somehow going to be combined with an arbitrary constant, you can relabel that as a new arbitrary constant. However, if this were t to the c, we could not rewrite t to the c as just c, because t is a variable. E is the constant 2.71728, I think, is Euler's number. So Euler's number is a constant. It's a well-known constant. In this problem here, we're going to do, once again, the same thing. I see that I have a g of t, and I have my h of y. Now, h of y doesn't have to be y to the first power. It could be y squared, for example. In fact, let's go ahead and do that. So with a y squared in there, let's make things a little bit more interesting. So we don't always have to end up with natural log of y. But what I'll do once again is just divide the function of y over to the left-hand side. Make this 1 over y squared times dy dt is equal to e to the t. And now when I integrate both sides with respect to t, once again, this is the whole purpose of that division was just to cancel out the dt's and have the left-hand side be integrated with respect to y and the right-hand side with respect to t. So we have the integral of 1 over y squared dy equals the integral of e to the t dt. Now the integral of e to the t dt is just e to the t. And we said that we're not going to write the plus c1 and this plus c2. We'll just write one arbitrary constant. We'll leave it on the right. That way we save ourselves a step. Now 1 over y squared, you kind of have to write that as y to the negative 2 dy, and then you could use the power rule. But I also want to share with you, I'm not a big advocate of doing a ton of integration by hand, so you are welcome to use Wolfram Alpha on this. And let me go ahead and show you how you would compute an integral using Wolfram Alpha. So here we are. This is just wolframalpha.com. And this is a powerful calculator, if you haven't used this before. So it will do integrals. You can use the extended keyboard. You can even download, I think for a couple bucks, the app. But using the website is free. And you have different symbols in here, like the integral operator is somewhere in here. Maybe I'm just not. There it is, integral operator. You could either enter that in to say integral of, or if you don't want to search for it, you can just type in the word integral. And what we want to integrate is 1 divided by y to the power of 2 dy. Just simple as that. You'll be able to check your input to verify that it's what you wanted to input. Right up here, so it tells you, okay, good, that's exactly what I wanted to integrate, and it comes out to negative 1 over y plus a constant. But again, because for our integral, we have the constant on the left, or on the right, we don't need to add the plus c. So you can see that that's basically utilizing the power rule of integration. And so now I'll come back over here, and let me go ahead and grab this just so we have this in our document. So you are well aware that I am completely okay with this process of using Wolfram Alpha to help us out. All right, so here we have it, our integral. And so now our equation from the previous line is negative 1 over y equals e to the t plus c. So we do need to solve for y. One of the ways people often do this is they multiply both sides by y and then divide. But here's the thing. Or a nice little handy trick, if 2/4 equals 3/6, which I'm convinced that you believe, 1/2 equals 1/2, it is also true that the reciprocal of the left equals the reciprocal of the right. So that means 4/2, which is 2, equals 6/3, which is 2. Therefore, if I take the reciprocal of both sides and make the left -y/1 and make the right 1/e⁻t plus c, now I've just saved myself that step of having to divide things over. I'll just multiply both sides by -1 now, and I'll make this y equals -1/e⁻t plus c. And now we can satisfy our initial condition. We've got our general solution. This is general solution. Plug in 1 for y, plug in 0 for t. So -1/e⁻0 is 1 plus c. And to solve for c, well, I need to get that out of the denominator. So again, I'll do this reciprocal trick. So 1/1 equals 1 plus c over -1. And now I'll multiply both sides by -1 equals 1 plus c. And so if I subtract 1 from both sides, I'll get c equals -2. So that gives me the value of my arbitrary constant, and my final solution is y equals -1/e⁻t minus 2. And that's my final answer. So there are again multiple ways of how you can carry out the algebra. This is my way of doing it, but as long as you're performing legal algebraic moves, which is what I'm trying to emphasize here, you're going to be in good shape. Sometimes you may end up doing steps that set you back a space, but there's lots of ways to drive around the block. You could drive around the block 6 times before you've said, okay, I've driven around the block, or you could drive way out of your way and still drive around the block. But the point is there's multiple ways to get to the final destination. What we've looked at is both of these problems are what we call initial value problems. All that means is that we've given both a differential equation and an initial condition, and that's called writing an initial value problem. So the initial value problem was the original thing that we were trying to solve. And then the solution, y equals -1/e⁻t minus 2, that's a solution to this initial value problem. Let's go ahead and take a look at a modeling problem, and we'll go ahead and wrap this video up here shortly. Imagine you are buying your first house. You plan on purchasing a $200,000 home at an interest rate of 4%. So this is usually an annual interest rate. Your payment will be $955 per month. So let's add a little bit of detail here. If you're not used to working with interest rates, we'll make this 3% to keep the math a little bit cleaner. But if that's an annual interest rate, what that means is that every month you're going to be charged 1/4% on your balance. By the way, it's kind of a weird thing. We usually don't divide percentages into pieces, but this is how banking systems work. So if it's 3% and it's compounded on a monthly basis, let's say, then you're only going to pay a fraction of that percentage every month. Otherwise, 4% a month would be quite hefty on a big sum of money like this. Your payment simply wouldn't be enough. So you're paying about $955 per month on this one. And we want to write an initial value problem that models the above scenario. Now it's going to get tricky to try to keep track of just the balance over time. And the reason for that is because if you think about how this will work, you are going to start off with your balance of $200,000. Now that balance of $200,000, before your payment goes in, the bank always wants to charge you interest first. So what's going to happen to your current balance? This again, think about this bathtub analogy. This is how much money you owe. That's how much is stacked in the bathtub. And to that, they're going to add more because every month you're charged 0.25%, which is 0.0025 as a decimal, of your current balance, which is $200,000. So that means they're going to tack on the interest, but then you're going to make your $955 payment, and so hopefully in net your balance will go down. So 0.0025 of 200,000 better be substantially or at least lower than the 955. That actually comes out to $500. So this comes out to $500 in interest that you get charged as a fee just for having that loan. And so if you take $200,000 and you add $500 to it, but then you subtract 955, you've actually dropped your balance by $455. So now you have a balance of $199,545, I believe. That should make sense. Yeah. So this is your new balance at the end of that month. But now to calculate your balance after 2 months, you still have to now add on the interest of your current balance, which is now the $199,545, and subtract off your constant payment. And this gets a little bit tricky because in order to get this new balance, how did I get that? Well, that came from the last step. So once I get this balance, I'm going to have to use that in the next step to help me compute the remaining balance. So it's a little bit tricky to write a function for this because this input and this input are constantly changing. However, if I think about the bathtub analogy, and I'm not going to draw a bathtub, I'll just draw this rectangle, and I will think about this as my balance. I'll think about B as my remaining balance in dollars, and T will be a measurement of time in months since a loan was taken. This type of loan is called a mortgage. A mortgage is just a special loan that is intended for property. So let's think about this bathtub that's filled with a balance. So what's coming in? Well, what's coming in is interest. That's what's making your balance bigger. But what's making your balance smaller is payments. And because our dB/dt, its units, let's think about this. B is in dollars, T is in months. So we want to think about by how much is our balance going up or down in dollars per month. So what's coming in terms of dollars per month? Well, it's 0.25% of whatever our current balance is. So we have to take 0.0025 times whatever our balance is, but that balance is always changing, though the remaining balance at any given moment is given by the variable b. Your payments, which is what's coming out, is always $955 per month. And so in this case, if we take the net rate, what's coming in, the rate in, which is 0.0025b, minus what's coming out, which is the 955, both of which are in dollars per month. As long as I take dollars per month minus dollars per month, I'm going to end up with units of dollars per month. Now remember, this dollars per month is always changing because how much they charge you in interest depends on how big your balance is. And as your balance goes down, the amount of interest that's charged, 0.25% of 199,545, is smaller than, just slightly, than 0.25% of 200,000. So, with that said, we now have our model, and our initial condition is that at time 0, b of 0 is going to equal 200,000. That's your initial balance. Great, so now we want to analyze this model. Now this was a really simple rate of change model, even though trying to estimate the balances, which we could have done, but we would have had to use this recursive process where the next step follows from the previous step. Here we have this really simple model that just has to take into account how fast money is increasing your balance and how fast money is draining your balance, and an initial condition, and now we can use calculus to solve this. Now, notice again that the right-hand side depends on the dependent variable. So our Calc 2 methods would not work, but we do see that since the right-hand side doesn't contain a t, that automatically means that I can factor this into a function of t and another function of b, excuse me. So to solve this, and we want to find out when will you pay off the house at this rate, let me write the right-hand side as 1 times 0.0025b minus 955. One of the common temptations here is just to try to divide the 0.0025b over, but if you do that, you have to divide both terms by that quantity, so you would think you'd be getting rid of it, but here you would, and here you would be reintroducing it, so you'd still be stuck with a b on the right-hand side. So be careful when you do this stuff. When you're doing division with multiple terms, each term has to receive that same denominator. So here I have what we can call our g of t, and here I'll have what we call our h of, can't call it h of y because our dependent variable is called b, so our h of b in this case. So the thing containing the dependent variable, that term I'm going to divide over, no different. It's going to look a little nastier, 1 over 0.0025b minus 955 times dB dt equals 1 on the right. So now I can perform my integration with respect to t on both sides, my integral with respect to t on the right. And so there I have that cancellation, and I can see that I'm integrating with respect to b. So I don't really feel like using u substitution here to solve this. I'm going to go ahead and use Wolfram Alpha. So there I have it input in. Just be cautious that you have parentheses around the whole denominator. Always check the input entry to verify that what you put in is what you wanted to put in. And so here it comes out to 400 times the log of 0.0025b minus 955. Be aware that most technology, when they say log, they actually mean the natural log. And here you have to read that note each time. So in our answer here, we just want to make sure that that's the case, that we don't use log, the base 10 that we're used to, but the natural log version of it. And so this left-hand side comes out to 400 ln of 0.0025b minus 955. So nice step there. We get to save ourselves a lot of extra integration by having technology do it for us. And this one will come out to t plus c over here. Great, so we're almost there. The last steps are to divide over the 400 because we want to solve for the balance. In order to get this into our graphing calculator, so I have t over 400, or I could write this as t plus c all over 400, but with multiple terms, they each have to get divided by the 400. The reason I wrote it like this is because if you divide an arbitrary constant by a constant, this is still an arbitrary constant. So you know what? I'm just going to relabel this as c. I know it's using the same variable and the two c's are not the same. You could call it c1 if you prefer, but because it's still an arbitrary constant, I'm not really concerned about the original c value before the assignment. So here I'll have t over 400 plus c, and now I'm going to go ahead and exponentiate. Very, very common step in differential equations. So just make sure you exponentiate both pieces. And here we'll have 0.0025b minus 955 equals, and here again I'm going to break this up into e to the t over 400 and e to the c. And e to the c is kind of what we've called k. So I'm just combining a couple of steps here, but go ahead and write it out if it helps. Add 955 and divide by 0.0025. So I'll have b equals k e to the t over 400 plus 955 all over 0.0025. That's totally fine to leave it like this, but because when I divide two terms by a value, they both get divided by it, I can reduce this a little bit more, and it's kind of helpful to do this. You'll see why here in a moment. And 955 over 0.0025 is 382,000. And the cool thing here is that when I have a product of things, like for example 3 times 4 over 2, I don't divide, if this is multiplication, I don't divide the 3 by 2 and the 4 by 2. I could do 3 times 4, which is 12, divided by 2 is 6. Or I could divide the 4 by 2, factor out a 2 from the numerator, in other words, cancel out the 2's, and I'd have 3 times 2, which is 6. Or I could take 3 divided by 2, which is 1.5. 1.5 times 4 is 6. So what I'm saying here is if I divide k by 0.0025, well, that's an arbitrary constant divided by a constant, and so that just forms a brand new constant. Again, I'll just relabel it k because I'm not concerned about keeping track of all the variations of that constant. So I can write this as k e to the t over 400 plus 382,000. Now, my initial condition needs to get satisfied. My initial condition was that b of 0 is 200,000. And pivoting off of that fact, I'll go ahead and replace my balance with 200,000. I'll replace t with 0. So I'll have k e to the 0 over 400 plus 382,000. E to the 0 is 1. K plus 382,000 equals 200,000. So if you subtract that over, notice that this is a case where the value of k, I think we observed this one other time in this video lesson, but the value of the arbitrary constant did not come out to 200,000 as it would have in a Calc 2 class. And that is because the method that we're using is different, and where our arbitrary constant ends up is not as a standalone term, but it ends up actually being a multiplicative piece, something that actually multiplies, and therefore its value ends up being different. So my final function, b of t, your balance as a function of time, is given by negative 182,000 e to the t over 400 plus 382,000. Finally, we are going to figure out for what t is b equal to 0. And why do we want to ask that question? Because we want to know when is the balance going to reach $0. So I'm going to come over here and go to Desmos and answer this question using technology. So here I'm going to type in negative 182,000 plus e to the x over 400 plus 382,000. And I could give this a name. I could call this f of x or even b of x if I want. The reason b of x will be handy is if you wanted to look at a table of values, notice that it calls the input x1. So if you come over here and you call this b of, you can't do b of x because x is a variable, but x1 represents the values of that variable. So for example, if I look at times 0, well, perfect. That's exactly what I wanted. This says that the function outputs 200,000. And as you increase this input, you can see your balance is going down every month because you are making payments. It will show the ordered pairs on the graph. The reason I'm not seeing it on the graph is because, first of all, my balance starts at 200,000. So you can see there it is. And it takes a long time to pay off the house, so I probably should go out. This is in months. 30 years is typically 300. Well, it is 360 months, but 30 years is usually how long a mortgage is paid off for. I don't really need to see all these ordered pairs, so I'll just uncheck that. And my balance, you can see, more and more rapidly drops, and it takes about 297 months before I've reached a $0 balance. So, balance as a function of time we've just found that it takes just under, about 25 years to pay off this balance. So here is the balance, and here is time, and we could say B takes about 297 months. And we'll go ahead and stop the video here. I wanted to make sure that we had an opportunity to do some modeling and solve a modeling problem, and hopefully you're now aware of the fact that solving differential equations, modeling with differential equations, is much more straightforward process than trying to solve a differential equation by just trying to take stabs at the solution.